I welcome all of you to today's lecture on atomic structure and bonding. And I'm saying this course unit contains two components. The first component is atomic structure, and the second component is bonding. Atomic structure and bonding. And what we are going to begin with is atomic structure. Atomic structure. But I would like to remind you that our present day knowledge of the word atom has got a beginning, it has got a foundation. There are earlier scientists or earlier chemists who came up, who formulated this word atom. This word atom. And one of these chemists was called Dalton. And he formulated what we call Dalton's atomic theory. Dalton's atomic theory. Now, Dalton, in his view of what an atom is, came up with four main points in his theory. He looked at all matter. Remember, matter could be in several states. Matter can exist in several states, such as the solid state. The solid state. Matter can exist in the liquid state or in the gaseous state. The gaseous state. So Dalton was looking at what matter is composed of. From your earlier science, you know that materials or matter could be in solid form or in liquid form or in gas form. And Dalton's interest was in the smaller particles which combine together to form that solid. The very tiny particles which combine together to form that liquid. The very tiny particles which combine to form a gas. And he came up with a point which is one of the most important points in his theory, and he said that matter is composed of tiny indivisible particles. Matter is composed of tiny indivisible particles known as atoms. So in Dalton's atomic theory, the major idea that we note is that matter consists of tiny indivisible particles which are known as atoms. And what I want to note here is the word indivisible. It means undivided, cannot be divided. According to Dalton, the particles, the tiny particles of which matter is composed, cannot be divided any further. That was during Dalton's time, that these small particles known as atoms, they are the smallest which can ever exist, but they cannot be divided any further into more smaller particles. Another point we note from Dalton's atomic theory is that the atoms or the particles of matter, in this case, i.e. the atoms, can neither be created nor destroyed. The particles of matter can neither be created nor destroyed. So, according to Dalton, the tiny particles of which matter is composed can neither be created nor destroyed. They can neither be created nor destroyed. In other words, they are indestructible. These particles are indestructible. According to Dalton, the particles cannot be destroyed. They can neither be created nor destroyed. They are indestructible. That one is another point to note in Dalton's atomic theory. We are going to see as we continue to move that some of these points in Dalton's atomic theory no longer apply to today's chemistry or to today's science because of several new discoveries which conflict or dispute Dalton's points or Dalton's atomic theory. But what is important for us to note is that Dalton was one of the earlier chemists who provided us with a good foundation of the present day chemistry. Without their efforts, maybe chemistry would not have reached the modern era, the modern chemistry era, which we are enjoying. We also need to note another point under Dalton's atomic theory. Now, according to Dalton, the smaller particles, which he calls the atoms, combine, they can combine with one another in a definite proportion. In a definite proportion. For example, let me give you a simple example which you already know of a gas which we call carbon dioxide. Carbon dioxide. Normally written as CO2. That is the formula of carbon dioxide. Now, according to Dalton, carbon dioxide gas is composed of an atom of carbon, which is one, but this one atom of carbon combines with the two atoms of oxygen, So Dalton's tiny particles or atoms combine in a certain proportion or a certain ratio. For example, 1 to 2. One atom of carbon combining with two atoms of oxygen, forming one molecule, which we call carbon dioxide. So, according to Dalton, the simple ratio must always be maintained, the simple ratio of combination of the atoms of different elements must always be maintained. Like one carbon should always combine with two oxygen atoms. The same story with the water. Water, which you already know from your earlier science, that it has a molecular formula of H2O. According to Dalton, the ratio in which the atoms of elements which make up water combine should always be two atoms of hydrogen combining with one atom of oxygen to make a water molecule. So the ratio of 2 to 1, two hydrogen atoms to one oxygen atom in water, or the ratio of one carbon atom to two oxygen atoms in a carbon dioxide molecule must always be maintained. That is the simplest ratio with which those atoms combine. So in the future, we will see what we call empirical formula, and also what we call molecular formula. Molecular formula. All substances, solid, liquid, or gas, can be expressed by writing their simplest formula, which shows the simplest ratio in which the atoms combine with one another to form a molecule of that compound. Or we can represent a compound or a gas, a liquid, or a solid with its molecular formula. Molecular formula showing all the number of atoms, within a molecule or within a compound that combine together to form that substance. So without going further into empirical formula and molecular formula, I want just to remind you the third point in Dalton's atomic theory. According to Dalton, atoms of the different elements of the different elements atoms of the different elements in a compound combine in or with a simple let us say in a simple proportion, in a simple ratio, or proportion. Atoms of the different elements in a compound combine in a simple ratio or proportion, meaning an atom of hydrogen can combine with, two atoms of hydrogen can combine with one atom of oxygen to form a water molecule. The ratio of combination there is 2 to 1. One atom of carbon can combine with two atoms of oxygen to form one molecule of water, and the ratio there is, one atom of carbon can combine with the two atoms of oxygen to form one molecule of carbon dioxide. The ratio of combination is 1 to 2 in carbon dioxide. Our duster is where? So to continue with the Dalton's atomic theory, there are a number of new discoveries which have come up, which I'm going to talk about. These new discoveries um, are here. So we are talking about the modern definition of an atom, of an atom. Now, presently, we know that what Dalton explained or described in his theory, some of these things do not apply. For example, Dalton says an atom is indivisible, and the atom cannot be divided any further. This means that there is some dispute which we now observe right now, because we know that an atom contains smaller particles in it, which are known as the subatomic particles. They are smaller units within an atom, which we call subatomic particles. For example, in the center of an atom, we know there is a nucleus. And within the nucleus, we find particles, which we call the nucleons. particles which we call the nucleons. Nucleons. And those nucleons are inside an atom. They are located within the nucleus of an atom. They are divided into two forms. The first nucleon or nuclear particle in an atom is called a proton. We call it a proton. Remember, Dalton said that an atom cannot be divided any further. It is indivisible. But modern chemistry says that an atom can be divided further because within the center of an atom, there is a nucleus with protons which carry a positive charge. The protons are positively charged subatomic particles in the nucleus of an atom. Then the second group of particles in the nucleus of an atom do not carry charge. Sorry, we give them a name, neutrons. They are called neutrons. So the second group of particles in an atomic nucleus are the neutrons, and these have no charge. They are non-charged. They do not have a charge. Remember, Dalton says an atom cannot be divided any further. Modern chemistry says an atom can be divided further, where we can identify the center of an atom with the two particles, which are the protons, and the second particle, the second group of particles are the neutrons inside an atomic nucleus. And outside the nucleus of an atom, there are several orbits or shells, or what we call energy levels, in which tiny particles with negligible mass are situated, in which they are located. So these tiny particles are known as the electrons. They are found where? Outside the nucleus. They are found outside the nucleus, but they keep on revolving, moving around the nucleus in what we call circular paths, known as orbits. The circular paths are known as orbits, and the orbits make up what we call energy levels. Energy levels. Energy levels, or we can call them shells of electrons. So what do we mean here? What we mean is that an atom contains a third group of particles which are found outside the nucleus, and those ones are what we call the electrons, because they carry a negative charge. They are negatively charged subatomic particles. They are negatively charged subatomic particles. They are negatively charged subatomic particles. So those are electrons. This means that the current structure of an atom is no longer the one which was described by John Dalton in the earlier years. Although we know that Dalton gave us a good beginning, a good foundation to understand what an atom is and the nature of an atom that makes up matter. Going back to the modern structure of an atom, I'd like us to focus on two things. One is the charge of the charges of the subatomic particles, and number two, the masses of the subatomic particles. When we understand those two, the charge and the mass of the subatomic particles, we will be able to get the correct modern definition of what an atom is. So let us focus on the first group of atoms, which we've called the protons. Which we've called the protons. The protons. Protons, as I have told you, are a group of particles in the nucleus. They are found within the nucleus, for which reason we call them the we call them nucleons. So protons are a group of nucleons because they are found in the nucleus of an atom. The second group is known as the neutrons. These neutrons are also nucleons because they occur inside the nucleus of an atom. Now, concerning the charge of these particles, I have just said that the protons carry a positive charge. They are positively charged. While I have said that neutrons carry a zero charge. In other words, they are non-charged. They are non-charged. Going to the mass, the mass of a proton is approximately one atomic mass unit. Atomic mass units. Approximately. While the neutron is also approximately one atomic mass unit. Now, that is inside the nucleus. What about outside the nucleus? So this one, which we've talked about, is in the nucleus, inside the atomic nucleus. That is what we have. We have nucleons, which are protons and neutrons. Protons carry positive charge and neutrons carry zero charge. The mass of a proton is approximately one atomic mass unit, and that of a neutron approximately one atomic mass unit. Now, if we go outside the nucleus, we find a group of particles which we've called electrons. Electrons. In terms of charge, electrons carry a negative charge, but the mass is too small of an electron. The mass is too small. This means it is in 0.00000 something. So the mass of an electron is too small, and therefore it is negligible. We can neglect it. By the word negligible, we mean that the mass is approximately zero. It is approximately zero atomic mass units. Going back to the atomic structure which I've described for you, I said that in the nucleus there are protons and neutrons. Then outside there are electrons. If you keep in mind the mass and the charges of the atom that we have talked about in that table, you can see that the greater mass of an atom is concentrated in the center. The mass of an atom is concentrated in the center in what we call the nucleons. So the nucleons make up, they constitute the bulk of atomic mass. The bulk of atomic mass. So, the greatest mass of an atom, actually, all the mass of an atom is concentrated in the center within the nucleus. Remember that the electrons which are in shells, the electrons which are revolving in orbits or in shells outside an atom do not carry any significant mass. The mass they carry is too small. The mass carried by an electron is too small and therefore negligible. It is negligible. So this means that if we are talking about the mass of an atom, the mass of an atom, the mass of an atom, which we can call the atomic mass, the atomic mass. The mass of an atom or atomic mass is concentrated in the center, in the center or in the central nucleus, in the central nucleus of the atom. The mass of an atom is concentrated in the central nucleus of that atom. So, this means that outside the nucleus, the mass is too small and therefore negligible. We can neglect it. We can approximate it to be zero. The mass of all the electrons in an atom. Now, that is about the mass of an atom. Talking about the size of an atom. Now, in chemistry or physical or inorganic chemistry, we mainly use what we call the atomic radius to determine the size of an atom. The size of an atom is determined by the atomic radius. And I want you to remember what we call a circle. A circle, we are going to show you what we call the radius of a circle. I'm saying the size of an atom is determined by the atomic radius. This means that if the radius of an atom is large or long, then the size of that atom will also be large. But if it is a small atomic radius, even the size of that atom will be small. For example, a small atom like hydrogen, which has only one proton and one electron, has got small atomic radius and therefore small atomic size. When we talk about a large atom like calcium with 20 protons and 20 electrons, the atomic radius of calcium is large or long, making that calcium atom also very long. So the size of an atom is not determined by the protons or neutrons, but it is determined by the electrons which are outside the nucleus. The nucleus is just a smaller, a smaller piece, smaller in size, but very heavy in terms of atomic weight or in terms of atomic mass. But when we come to size, the size is very small for the nucleus. The electrons which are many outside the nucleus are the ones which determine the size of an atom. So we are saying the size of an atom is determined by atomic size, is determined by the number of electrons, by the number of electrons in an atom. So it is not the protons or neutrons which determine the size of an atom. It is the number of electrons. The more electrons an atom is, the bigger the size. The fewer electrons, the smaller the size. So we are saying that large atoms of elements, large atoms of elements such as lead, Pb, or silver, Ag, contain more electrons than smaller atoms of elements like hydrogen, which is H, and maybe carbon. So if we are to compare the atomic size is compared on the basis of the number of electrons in an atom. We use the number of electrons in an atom to compare the atomic size. A large element, an element which is large in size, such as lead or silver, contains more electrons than an element which is smaller in size, like hydrogen and carbon. So I've brought out these points to emphasize two issues. The first issue is that atomic mass is it depends on how heavy the nucleus of an atom is. If the nucleus has got more protons and neutrons, then that atom will be with a large atomic weight or large atomic mass. But the particles which we see outside the nucleus do not contribute to the mass of that atom. They only the electrons only contribute to the size of an atom, which is determined by the atomic radius. So if we are talking about a circle, for example, a circle like this, the circle has got the center of the circle. So if we are looking at an atom, that center of the circle is like the nucleus. It is like the nucleus. And now, from that center going to the circumference of the circle, that is what we call the radius. The radius. So, in order to understand atomic size, if the element is a large element such as silver or lead, the outermost shell, which is occupied by electrons, will be far away. It will be very far away from the nucleus. And the electrons in the outermost shell will be very separated, distant, a long distance away from the nucleus. So this will be an electron in the outermost shell. In the outermost shell for a large atom. For a small atom like this one, suppose this one is maybe carbon and this one is silver. In terms of size, the outermost shell will have of carbon will have an electron. This will be an electron in outermost shell or outermost energy level. So for a small atom such as carbon, the size of that atom is determined by the atomic radius. In other words, the outermost shell contains electrons which are closer, which are nearer to the nucleus. What about a large atom? A large atom, the outermost shell will contain electrons which are very far away from the nucleus. So in this case, the atomic radius is larger. The atomic radius is larger in a large atom. But in a smaller atom, the atomic radius is smaller. And we are using the outermost shell. We are using the electrons in the outermost what? Shell to determine the size of the atom. So if the electrons of the outermost shell, like a carbon, which you know, atomic number is 6, and the electronic configuration is 2 to 4. It means the innermost shell contains only 2 electrons, 1 and 2. Then the outermost shell contains 4 electrons, 1, 2, 3, and 4. That is for carbon. That means that the electrons in the outermost shell are nearer to the nucleus. This is important. I'm emphasizing it, nearer, because the nucleus contains protons which are positively charged. Therefore, the charge of the nucleus is positive. The charge of the nucleus is positive. What about the charge of the electrons? The charge of the electrons is negative. The electrons are negatively what? Charged. Therefore, it means there is always a force of attraction, a pull, and we call it electrostatic force. We call it electrostatic force of attraction. Electrostatic force of attraction. There is always an electrostatic force of attraction between the electrons in the shells and the nucleus, which is positively charged. So the positive nucleus will always attract the electrons in an atom. So if the outermost electrons are far away from the nucleus, then the nuclear attraction will be lower. So in a large atom, the electrons are far away from the nucleus. And those outermost electrons experience very small nuclear attraction. They are not attracted greatly by the nucleus because of the large size of the atom. They are far away, the outermost electrons. In a smaller atom, the electrons are near to the nucleus. Therefore, the nuclear attraction, or something we call nuclear charge, the nuclear charge and nuclear attraction is great in a smaller atom. So the size of the atom will be kept small. Why? Because of a strong nuclear attraction of the outermost electrons. Here in silver, the size of the atom will be large. Why? Because of a weak nuclear attraction of outermost electrons by the nucleus. So these two, you should understand them properly, that the size of an atom depends on the number of electrons in that atom. If there are many electrons in that atom, the nuclear attraction for the outermost electrons will be small, and that weak nuclear attraction will lead to large size. When the atom is small, the nuclear attraction for the outermost electrons will be great, leading to a contracted size, a smaller size. So let us now go back to maybe the numbers. Now, in any atom, we are talking about the numbers of the particles, the numbers of the subatomic particles. In any atom, the number of protons in the nucleus is always equal to the number of electrons outside the nucleus. That is a fact. In any atom, and that atom is described as electrically neutral. In an electrically neutral atom, in other words, what I'm calling electrically neutral atom, it is that atom which does not carry any charge. An atom which has zero charge. It is neither positively charged nor negatively charged. So we call it electrically neutral atom. Or we can say a non-charged atom. We can call it a non-charged atom. So in an electrically neutral atom or a non-charged atom, normally the number of protons in the nucleus, atomic nucleus, is always equal to the number of electrons outside the nucleus. Is always equal to the number of electrons outside the nucleus. That is the relationship we should never forget. When an atom has no charge, for example, if it is like a carbon without any charge, it is not maybe carbon plus, it is not carbon 2 plus, it is simply carbon without a charge. So if it is silver, if it is Ag, this is called electrically neutral atom. Why? Because it is not Ag plus. If it is Ag plus, then it is no longer an electrically neutral atom. Are we there? It is no longer an electrically neutral atom. But if it is non-charged, simply as Ag, then we call it electrically neutral atom. So in an electrically neutral atom, that is an atom without a charge, the number of protons inside the nucleus is always equal to the number of electrons outside the nucleus. We can convert this statement by saying that the number of positive charges, because protons are all positively charged. So the number of positive charges is equal to the number of negative charges is equal to the number of negative charges outside the nucleus. This means if we take an example of carbon, which I've already given you, we can say in carbon, for example, in carbon, the number of protons, which is 6, the atomic number is the number of protons, in the nucleus of an atom. So in carbon, for example, we have 6 protons, and that means that if there are 6 protons inside the nucleus, there are also 6 electrons outside the nucleus in shells or in energy levels. So in carbon, which is electrically neutral, in unelectrically neutral carbon, there are 6 protons and also 6 electrons. In other words, there are 6 positive charges in an atomic nucleus of carbon and 6 negative charges outside the nucleus of carbon. And now, it is this relationship, it is the relationship of protons and electrons which makes an atom to be electrically neutral. Because from mathematics, we know that if you get positive 6 and you add there negative 6, the answer will be 0. Isn't it? It is. If you have 6 protons with a positive charge in the nucleus and 6 electrons with a negative charge outside the nucleus, the positive charge, which is equal to the negative charge, they cancel out, and we remain with a net charge of 0. We remain with a net charge of 0 in an atom. So what we call an electrically neutral atom, uh, is said to be non or zero charge. Why is an atom? Why is an atom described as electrically neutral? Electrically neutral. That is a question which can be posed to you. Why is an atom described as electrically neutral? The answer here is that the net charge of an atom is 0. The reason is that the net charge of an atom is 0. Why? Because the number of protons, with positive charges in the nucleus is equal to the number of electrons, is equal to the number of electrons with negative charges outside the nucleus. Outside the nucleus. So in the ongoing discussion, I have labored to give you the concepts, the main concepts, which form the definition of an atom, the modern definition of an atom. And we are now going to use these concepts to define an atom. Remember, our course is known as atomic structure. What therefore is an atom? So if we go away from Dalton's atomic ideas and we come to the modern ideas in chemistry that I have already shown you, that an atom can be divided further into subatomic particles. We can now define it like this. We can say we define an atom as the smallest electrically neutral particle of an element that can take a part in a chemical reaction. That can take part in a chemical reaction. An atom is the smallest electrically neutral particle of an element or of matter that can take part in a chemical reaction or in a chemical change. Remember, from Dalton's ideas, atoms can combine with one another in simple ratios or in simple proportions, forming compounds, or forming molecules of that substance. So in this case, this is the definition which we shall move with of an atom. We will no longer say that an atom is indivisible or an atom is indestructible. No, we will say an atom is simply a small electrically neutral particle of an element, and that particle can take part in a chemical reaction, meaning one can combine with another. One atom of an element can combine with an atom of another element, forming a new substance, like a compound. So let us also define the other subatomic particles. Other definitions of subatomic particles. The first one, I've said there is a term we call nucleons. And nucleons are the particles in the nucleus of an atom. These are the subatomic particles. They are the subatomic particles. They are the subatomic particles in the nucleus. The subatomic particles. I don't want to repeat the word in the nucleus of an atom because I've used the word subatomic. They are the subatomic particles in the nucleus. And remember, there are two types or two forms, two categories, two forms of nucleons in an atom, which we've already seen. The first one are the protons, and the second one are the neutrons. So within the nucleus, there are protons and neutrons. So let us define each one of them as we build our science of atomic structure. As we build our science of atomic structure, let us talk about those nucleons one by one. So we've said the protons are subatomic particles with a positive charge. So we shall say protons are positive they are positively charged, subatomic particles in the nucleus. Protons are the positively charged subatomic particles in the nucleus. I've already talked about they have a mass of approximately 1 atomic mass unit, and they have a charge of +1. They are positively charged. If they are 13 protons, then that is positive 13 positive charges. If it is 1 proton, like in hydrogen, that is only 1 positive charge. The second nucleon is the neutron. The second nucleon is the neutron. And the neutrons we can say zero charged. We can say zero charged. They are zero charged, or we can say non-charged. Non-charged subatomic particles. Subatomic particles in the nucleus. In the nucleus of an atom. So we are building these concepts from the explanation that I have already given you. The neutrons, I've also said, their mass is approximately equal to the mass of protons, and they carry no charge. This is why I am still emphasizing that the mass of an atom, the atomic weight, is concentrated in the center, in the central nucleus, because neutrons have a mass almost equal to that of the protons, So meaning neutrons, they are heavy in the nucleus. Even protons, they are heavy in the nucleus, and together they constitute, they form the atomic weight. So the atomic weight is in the central nucleus. Going back to our third group of subatomic particles, we can define them as negative electrons. They are negatively charged subatomic particles. They are negatively charged subatomic particles located where? Located in shells, or energy levels outside the nucleus. Electrons are negatively charged subatomic particles. Where? Outside the nucleus. And we find them in shells or energy levels. But there is a new word which I want to introduce here, and that word is known as orbital. When we are describing an electron, we are interested in the particular location of that electron, because we've seen that the energy level is something which is large. For example, the whole of this orbit, like that one is an energy level, a shell. But are electrons in the hollow shell? No. The electrons can be located somewhere within the shell in a specific place, which we call the orbital. So I want to introduce that word, orbital, when we are describing electrons in an atom. That word is orbital. Orbital. We define an orbital as a volume of space around the nucleus. A volume of space around the nucleus where there is a high chance of locating an electron. An orbital is space around the nucleus, or we can say it is a volume of space where around the nucleus where there is a high probability of finding an electron, of locating an electron. So that word is important, orbital. Remember, the energy level or the shell is something which is very large, something which is large in size. But where exactly can we locate an electron? Where exactly can we find an electron outside the nucleus? That electron can be located outside the nucleus in a specific place, in a specific volume of space known as an orbital. Remember, that an electron is never in one place. It is never static. The electrons keep on revolving around the nucleus. And as the electrons are revolving around the nucleus, I have already told you, they are revolving with a negative charge. And the positive nucleus always keeps on attracting them as they're moving or revolving around the nucleus. So that nuclear attraction uh, is experienced whenever an electron is moving around the nucleus in a circular path known as an orbit. But the specific space, the particular place where we locate an electron around the nucleus is called an orbital. And I'm going to show you some examples of orbitals, examples of energy levels. Energy levels. You may not have met this in your O level, but I'm briefly going to talk about it to guide you in how we can write electronic configuration. Examples of energy levels and sub. Okay, examples of energy levels, comma, sub energy levels and orbitals. Orbitals. This is important for you to know. If we are talking about a small element, we are talking about a small element like maybe carbon. Let me again give an example of carbon. That carbon has got what you call an energy level. It also has what you call sub-energy levels and orbitals. So I'm going to first of all show you the forms of energy levels. Forms of energy levels. The first one we can call it N is equal to 1. N is equal to 1. That is the first energy level, which is very close to the nucleus. The first energy level, N is equal to 1. It is very close to the nucleus. This is the first energy level. energy level which is nearest or closest to the nucleus. So as we are moving away from the nucleus, we go on numbering the energy levels as n is equal to 2. From n is equal to 2, we go to n is equal to 3, like that. So depending on the size of the atom, if an atom is small, it can have only one energy level, n is equal to 1. If an atom is large, like a calcium, it can have like 3 energy levels. From n is equal to 1, n is equal to 2, n is equal to 3. So depending on the size of the atom of an element. So the second one is n is equal to 2. So this means this is the energy level after n is equal to 1. The second energy level. Are we there? So this is the second energy level after the innermost shell. The second energy level or this after n is equal to 1 after the innermost shell. We can have another one, n is equal to 3, etc. and many others, and many other energy levels depending on the size of the atom. Depending on the size of, the atom. So if it is a large atom, then there will be many energy levels. If it is a small atom, there can be only 1 or 2 energy levels. Now, what do we find in energy levels? In energy levels, these are forms of energy levels. N is equal to 1, N is equal to 2, and so on. Now, we have what we call sub-energy levels. Sub-energy levels. Sub-energy levels. Now, in the first energy level, there is only one sub-energy level. In the second, there are 2 sub-energy levels. So let us give an example. In n is equal to 1, in n is equal to 1, there is only one sub-energy level. There is only one sub-energy level. There is only one sub-energy level. And that one sub-energy level is called 1s. It is called 1s. It's called 1s. So this means that, let me give an example. A small atom like hydrogen, a hydrogen atom, which has got atomic number 1, which has got atomic number 1, which has got atomic number 1, hydrogen atom with only atomic number 1. It means it is a very small element. Hydrogen is the smallest element we know, the lightest element, lightest, not heavy, but lightest. So hydrogen, the lightest element we know in the periodic table, contains only 1 proton in the nucleus. It contains only 1 electron outside the nucleus. And when we are writing the electronic configuration of hydrogen, we put that 1 electron on top of 1s. So we shall write electronic configuration. This is not all level work because O level will tell you the electronic configuration is only one, like that. But here, as we advance in chemistry, the electronic configuration is now written in terms of energy levels and sub-energy levels and orbitals. So we will say the electronic configuration of hydrogen is one, meaning one means what? It means the first energy level, which is nearest to the nucleus. Then we will put there S. S means what? The sub-energy level in that n is equal to 1. Then on top, we write figure 1 like this. We write figure 1 like that. 1, 1, S1. That is the electronic configuration of hydrogen. Meaning, there is one principal energy level or principal quantum shell. There is one sub-energy level, and that one sub-energy level contains one orbital, which is called the s orbital, with one electron. For hydrogen, let us build the story. Let us build the story. Consider helium with atomic number 2. Helium, which is a noble gas, helium, which is a rare gas or a noble gas, has atomic number 2, has atomic number equal to 2. So how do we write the electronic configuration of helium? Because helium also has only one energy level. So we are going to write the electronic configuration of helium, the electronic configuration of helium, we'll simply write it like 1s2. 1s2. What does it mean? It means that the S sub-energy level can be filled up to a maximum of 2 electrons only. So when you fill 1s2, don't add there the third electron. There is no 1s3 because 1s and any orbital of s can only hold a maximum of 2 electrons, and it is the one which is the first. It is the first sub-energy level in any energy level, in any quantum shell. S is the first energy level, and it can hold a maximum of how many? Only 2 electrons. So let me emphasize that point by saying that the S orbitals, or the S sub-energy level can only hold a maximum of 2 electrons. A maximum of 2 electrons. So this means that if we are talking about a hydrogen like this H atomic number is equal to 1. It has only one S, 1 with 1 electron. So we can draw the electron, the way the electron is found like this, simply by writing like this. The arrow could be written upwards or downwards, but an electron in an orbital is always written with an arrow like this. So if we are talking about helium, atomic number is equal to 2. Remember the electronic configuration is 1s2. 1s2. If we are to draw the orbitals in helium, they will be like this. It will be one electron like this, and another electron facing downwards. Normally, electrons, when the two electrons are on the same orbit and they are facing one another. For example, if we have electrons facing one another like this, with the arrows pointing to the same direction, this is impossible. This is impossible. It can never take place. Why? Because both are negatively charged. This one is negatively charged and this one is negatively charged. So they would repel one another. Like forces repel and like forces attract. So the only way the two electrons in a helium atom can arrange themselves is with opposite spins. These are two electrons in an orbital. But we say they have opposite spins. Opposite spins. They should not face one another. One should face up, another electron in the same orbital should face downwards with opposite spins to avoid electron repulsion, because both of them carry a negative charge. Both of them are negatively charged. So this is for smaller elements, which have only one energy level, n is equal to 1. Let me show you other elements where we have like n is equal to 2, where we have two energy levels, So number 3, we stopped on number 2. We are going to lithium. Lithium is known as an alkali metal. We call it an alkali metal. It is found in group 1 of the periodic table. So we call it an alkali metal in group 1 of the periodic table. Lithium, an alkali metal, in group 1 of the periodic table. Actually, the group 1, sometimes we put there A, we say 1A. Group 1, 1A of the periodic table. All alkali metals are in group 1A of the periodic table. And we are saying that its atomic number is 3. The atomic number of lithium is 3. But I have already told you a rule. The rule is when you feel 1s with the 2 electrons, stop there. It's already full. It's already maximum. Now move to the second energy level. So in this case, we are going to say the electronic configuration of lithium will be 1s. This is the innermost shell, which we said has a maximum of 2 electrons. From that, we move to the second energy level, which will begin with the 2. So we are now on n is equal to 2. The second energy level. But in lithium, they should be 3 electrons. If the first 2 electrons are occupying 1s energy level, then it is only 1 remaining electron. Out of the 3, 2 are filled. So we are now going to fill the third. So it means that in the second energy level, there is only 1 electron. So that is what we write as 1s2 to s1 as the electronic configuration of lithium. In O level, this is what will be written as 2 to 1. This one will be written simply as 2 to 1. In advanced level and university level, we no longer write it as 2 to 1, but we also indicate, we also show the specific orbitals, the specific energy level and sub-energy levels where the electrons are found. So here it is 1s2, it means the first energy level with 1s sub-energy level. Then 2s1, it means the second energy level. But remember, every energy level begins with S. With S. So there is a 2s1. Or simply 2 to 1 for lithium. If I can diagrammatically show those electrons, how they are arranged, I will say 1s2, I will draw it simply like this. I'll draw it with one electron facing up and another electron facing down. That is 1s2. Then the second one is 2s1. Then I'll draw only one orbital. I'll draw only one orbital with only one electron like this. Now I want to teach you another concept, and that concept is called the ground state. The ground state electronic configuration. That word ground state electronic configuration means the state of an atom when it is not excited, when the atom is electrically neutral, when the atom has not combined with any other element, when the atom is zero charged. The electronic configuration is called the ground state electronic configuration. So we call it the ground state electronic configuration. To emphasize that, if somebody tells you, write the ground state, the ground state electronic configuration, electronic, it should not confuse you. That word ground state should not confuse you. If they tell you, write the ground state electronic configuration of lithium, you simply write the way we wrote there, 1s2, 1s2, 2s1. That is the answer. The ground state electronic configuration. It means the atom is not excited, the opposite of ground state. The opposite of ground state is excited. That is when the atom has reacted with another element. We call it the excited state. And when an atom is in this excited state, it is no longer electrically neutral. It is no longer zero charged. It will have either negative charge or a positive charge. We will say the atom is in excited state. And it will acquire a new name. It will be called an ion. An ion. If it is in excited state. But if it is in the ground state, then that atom carries no charge. That atom carries no charge in the ground state. Let us build the story so that the science comes out properly. The science of ground state electronic configuration. The fourth element we know, which has got atomic number, atomic number 4 is beryllium. Beryllium is described as an alkaline earth metal. It is an alkaline earth metal in group 2A of the periodic table. In group 2A of the periodic table. Now, beryllium has got atomic number 4. Beryllium has got atomic number 4, and Atomic number, remember, we represent it as 0. As got, not 0, as Z. Atomic number is Z. So if it has 4 electrons, if the atomic number is 4 in beryllium, then it means beryllium has 4 electrons outside the what? The nucleus. Now, to write the ground state electronic configuration, to write the ground state electronic configuration of beryllium, we will say 1s2 is the innermost shell, the innermost energy level. The second one, because there are 4 electrons in beryllium atom, then it means that we go to the second energy level, which is the 2s. And I said S must always have a maximum of 2 electrons. So since to make a 4, we are left with only 2 electrons. Those 2 electrons are put here. They are put there. So that is the ground state electronic configuration of beryllium. If I can diagrammatically represent this, it will simply be drawing one orbital of 2s, I mean of 1s there, with the 2 electrons pointing in opposite direction. And then I will also draw the second energy level, 2s, the second energy level with the 2 electrons. That gives the electron configuration of beryllium. I want to remind you that the number of electrons in the outermost shell make up the group number to which the element belongs. So we have said lithium is in group 1 of the periodic table. That means it has only 1 electron in the outermost shell. Secondly, beryllium, we've placed it in group 2 of the periodic table. That means the outermost shell of beryllium contains 2 electrons. It contains 2 electrons. We are building the story, and I want you to remember always that when we move from the S sub-energy level, the second sub-energy level we go to is called P. S is always the first sub-energy level in any quantum shell. Then, if the quantum shell is large, like n is equal to 2, it will have another sub-energy level called P, not S but P. So in this case, I'm saying that after the S sub-energy level, the next one, the next sub-energy level is called P. It is called P. And as a rule, P always has a maximum. Every sub-energy level has a what? A maximum. So P has a maximum. Let us use the word filled. P is filled with a maximum of 6 electrons. P is filled with a maximum of 6 electrons. In other words, it has 3 orbitals. It has 3 orbitals. These 3 orbitals can be written like this. So this is the P sub-energy level. This is the P sub-energy level. So we can write it as 1 can be filled with a maximum of 2. Another one can also be filled with a maximum of 2. And the last p orbital. The last p orbital can be filled also with the maximum of 2. So there are 3 orbitals at the p sub energy level. There are always 3 orbitals. One orbital with 2 electrons, second orbital with 2 electrons, and the third orbital with also 2 electrons. This means that the maximum number of electrons at the p sub energy level is 6. It is always 6 electrons. Let us give an example where we have a p orbital, like the fifth element of the periodic table is known as boron. We call it boron. For example, boron, let us call it number 5. Boron has got a symbol B. It is found in group 3 of the periodic table. In group 3 of the periodic table boron has atomic number 5. Atomic number is 5. This means that the ground state electronic configuration of boron, the ground state electronic configuration of boron will be, we shall begin with 1s2 followed by 2s2, and S is now full. Then we move to another sub-energy level at level 2. And that is called 2p1. 2p1. That is the ground state electronic configuration of boron. In other words, the first energy level has only one orbital, one s orbital, which we write like that. The second energy level has got a 2s sub-energy level with 2 electrons and a 2p. A 2p, remember 2p, they should be 3 orbitals. 1, 2, 3. But for boron, only 1 electron is found at this 2p sub-energy level. So this is boron. It stops here. So the second sub-energy, the second 2p has only 1 electron, which you write like that. Going to carbon, which is number 6. We're going to speed up because we want to keep the video a bit shorter. Carbon, remember carbon is a group 4 element in the periodic table. Sometimes we write it as group 4b. Right there, B, not 3a or 4a. In the periodic table. This carbon has atomic number 6. Therefore, the ground state electronic configuration of carbon will be, so we shall say 1s2, 2s2, 2p2, which will be diagrammatically 2 electrons in the 1s energy level or sub-energy level, then 2 electrons in the 2s sub-energy level at n is equal to 2, and only 2 electrons. So we will locate the 2 electrons by first writing 1 electron in the first orbital, and again write another electron in the next orbital. So we first write electrons one by one, singly, before we begin pairing. So instead of writing here as, instead of writing it as one electron and two electrons in the same orbital, we simply put one electron in one 2p orbital and another electron in the next 2p orbital. If it was, if we had more electrons, we would put the third one in the last 2p orbital, and then we would begin pairing. 4, 5, 6. So electrons first fill orbitals singly, one by one, before you begin pairing. That is a rule in physical chemistry and inorganic chemistry. It is a rule of filling electrons in orbitals. First fill one by one before you begin electron pairing. The story is interesting when we move to number 7, which is nitrogen. Nitrogen is a group 5 element in the periodic table. In the periodic table. And we are saying nitrogen has atomic number 7. What is the electronic configuration? The ground state electronic configuration of nitrogen will be 1s2, which is the innermost energy level, followed by the second energy level, 2s2, and the third energy level, sorry, the 2p sub energy level has electrons in a nitrogen atom. And we can diagrammatically show this by putting there the two electrons with opposite spins in the 1s orbitals, and then two electrons with opposite spins in the 2s sub-energy level. Remember, at 2p, we put there how many orbitals? 3 orbitals. And they are 3. But the rule says we fill the electrons one by one, singly, before we begin pairing. So that is 1. This is a 2. This is a 3. So nitrogen has got a half-filled 2p orbital, a half-filled 2p energy level, sub-energy level. Half-filled, because this is half-filled, half-filled, half-filled. So in the nitrogen atom, there is a 2p3, which is half of 2p6. Because we say for 2p to be full, there should be 6 electrons. So nitrogen has got a half-filled 2p outer sub-energy level. Oh, this is good. This is good. This is good. We are going to stop on element number 20 and we call it a day. And we call it a day. Can we speed up? Yes, we can speed up by going to oxygen, which is having atomic number 8. And it is an element in group. We know oxygen is a gaseous element. A gaseous element in group 6. In group 6b of the periodic table. The atomic number of oxygen is 8. It is 8. How do we feel the ground? How do we write the ground state electronic configuration? The ground state electronic configuration of oxygen is 1s2, 2p2, 2s2. Are we there? And then 2p4. 2p4. This means there is only one orbital, and at that energy level only one. Then here there are 2 electrons at the 2s sub energy level, and then we go to the 2p, 1, 2, 3, we can fill singly 1, 2, 3, but remember here they are 4. Already 3 are filled. So the fourth electron comes and we pair here in that orbital. So that is oxygen electronic configuration in the ground state. Fluorine in this is also a noble, not a noble gas. We call it a halogen. A halogen in group 7b. In group 7b of the periodic table. You may put there the B or you may not put it there, but for me, I prefer putting it there. So fluorine has got atomic number 9. Atomic number 9. And the ground state electronic configuration of fluorine will be 1s2, 2s2, 2p5, 2p5, 2p5. We have not yet filled the 2p. We have not yet filled the 2p because we said that 2p can only be filled with a maximum of 6 electrons. And so far we have filled up to 5. And the drawing of these orbitals will be 2 in 1s orbital, also 2 in the 2s orbital, and those are so far 4. Those are so far 4, but you want to make them 9. Want to make them 9. So we said if these are 4, then this is 5, this is 6, this is 7. Then we pair 8 and 9. So those are the electrons in the orbitals of fluorine. Moving to neon, which is a noble gas in group 0, group O, or group 8 of the periodic table. Remember, the group number is always the number of electrons in the outermost shell. The number of electrons in the outermost shell. So neon has atomic number 10. And the ground state electronic configuration, the ground state electronic configuration of neon will be 1 s2, 2 s2, and 2 p6. When we reach 6 at 2p, that is full. That energy level is full. And we say that element with a full outermost shell is chemically stable, chemically inert, and chemically unreactive. Chemically unreactive. So at this level, which is level 2, N is equal to 2. That level. There is N is equal to 2 has a maximum of 8 electrons. It has a maximum of 8 electrons. And when the N is equal to 2 has 8 electrons, we say that the atom has a completely filled outer octet. If they are 8, we use the word octet. If they are 2, like in helium, we say a completely filled outer duplet if they are two in helium. But if it is at this n is equal to 2 level, the outermost shell, having a maximum of 8 electrons, then we call it a completely filled outer octet. And this completely filled outer octet is said to be chemically stable, which is chemically stable. Chemically stable. So, and this makes the element chemically unreactive. Because the reason why elements combine with one another is to either lose or gain electrons to fill the outermost shell. But if the element already has a full outermost shell, like a full octet or a full duplet, as in the noble gases, then there is no need to undergo a chemical reaction. There is no need to combine with other elements because it is already happy. It is already filled. It is already full. The full outer octet makes it chemically unreactive or chemically inert. This is the reason why noble gases do not undergo chemical reactions. They do not react with other elements. Noble gases do not react with other elements. Why? The question says, why? Why do noble gases? Why do noble gases such as helium and neon, why do noble gases like helium and neon, why don't they undergo chemical combination? Why don't they undergo chemical combination? Why don't noble gases undergo chemical combination? Or why don't they undergo chemical reactions? The answer is noble gases have uh, full full outer octets. The answer is that noble gases have full outer octets or duplets. And therefore, they neither lose nor gain electrons in their outermost shells. In their outermost shell. This makes them chemically inert. Therefore, they are chemically inert. You will never find any element, you will never find any compound with the neon, maybe neon chloride. We don't have neon chloride. We don't have neon hydroxide. We do not have neon carbonate. We do not have neon nitrate. Why? Because neon does not combine with other elements. It already has a full outer octet. It already has a full outer octet, which is a chemically stable state. A chemically stable state. So in the ground state of neon or any other noble gas, the element is already chemically stable. It does not combine with other elements by either losing or gaining electrons. No, they are already chemically stable and chemically unreactive. or chemically inert. Let us move. The story is interesting. Sodium is an alkaline metal in group 1A. In group 1A of the periodic table. Of the periodic table. And we are saying sodium has atomic number 11. I'm going to speed up. This means we are going to write the electronic configuration of sodium as 1s2, 2s2, because the S sub energy level must have a maximum of only 2. Then we move to another 2p6. So this is similar to the one we've written for neon, but sodium is larger in size than neon. So it goes to another energy level 3. So we call it 3s. Because every energy level begins with S, which must have a maximum of 2 electrons. So for sodium, so far those ones filled are 4 plus 6. The remaining one is only 1 to make them 11. So that is the ground state electronic configuration of sodium. Magnesium is an alkaline earth metal in group 2. Is an alkaline earth metal in group 2 of the periodic table. In group 2 of the periodic table. In chemistry, that word periodic table carries a lot of meaning because all elements were arranged in an order, in an orderly manner, from the smallest to the largest, in the order of increasing atomic number. And that orderly arrangement of elements in the order of increasing atomic numbers is called the periodic table. And the periodic table is made up of the vertical columns, which are elements belonging to the same family, and they have the same number of electrons in the outermost shell, and that makes a group. So when you say group 1 of the periodic table, it means all the elements in that chemical family, in that vertical column, have 1 electron in their outermost shells, and so on. So we love that word periodic table as chemists, because the father of the periodic table, the founder of the periodic table, was called Dmitry Mendeleev. He did a big job of measuring these elements and arranging them in order of increasing atomic number, from the smallest or the lightest, which is hydrogen, to very large and large elements like lead, uranium, and so on. So they are arranged in an orderly and repetitive manner in increasing atomic number, in an order of increasing atomic number. They are organized in that table called the modern periodic table. So in the modern periodic table, magnesium is found in group 2A of the periodic table, and the atomic number of magnesium is 12, meaning that the ground state electronic configuration of magnesium is 1s2, 2s2, 2p6, and then we move to 3s, the third energy level, 3s2. When we fill the 2 electrons, if you add 2 plus 6, 8, 8 plus 2, 10, 10 plus 2, 12. That gives you the atomic number of magnesium, and therefore this is the ground state electronic configuration of magnesium. This is the ground state electronic configuration of magnesium. Oh, very interesting. Very interesting. The outermost energy level, the outermost energy level has 2 electrons, and that has placed magnesium in group 2 of the periodic table, confirming what I said, that the group number is always equal to the number of electrons in the outermost energy level. Let us go to aluminium, which is in group 3. This is also a metal. Is a group 3 metal in the periodic table. In the periodic table. Remember, as I'm writing the word periodic table, I am very happy as an inorganic chemist. Why? Because the periodic table in chemistry is a fundamental table, important table, with elements arranged in order of increasing atomic numbers, from the lightest to the heaviest element known on Earth. So aluminium has atomic number 13. Aluminium has atomic number 13. Therefore, the ground state electronic configuration of aluminium is 1s, 1s2, 2s2, 2p, 2p6. The 2p should have 6 maximum. Then we go to 3s, 2. But remember, these are 12 so far. And from S, sub-energy level, we go to 3p, sub-energy level, which is left with only 1 electron. So the third, this third energy level, N is equal to 3. In aluminium has 3 electrons. That N is equal to 3. That one which gives 3s, 3p. It has 2 plus 1, 3 electrons. It has 3 electrons. And that places aluminium in group 3 of the periodic table. The story is interesting when we go to silicon. Silicon is not a metal. Remember, metals are mainly found from group 1 to group 3. Group 1 to group 3. And the metals we know, they have like 1 electron in the outermost shell, 2 electrons in the outermost shell, or 3 electrons in the outermost shell. And during a chemical reaction, metals combine by losing the electrons from the outermost shell to form positive ions, which we call the cations. Those are metals. They have few electrons in the outermost shell, in the outermost energy level. But when they are combining with other elements, they give up, they lose those electrons, and they form positive ions during chemical combination. But when we begin from group 4, group 5, to group 6, up to group 7, group 4, group 5, group 6, up to group 7, those are called non-metals. They have more than 3 electrons in the outermost shell, and they prefer to combine with other elements by gaining. Because they already have many electrons in the outermost shell, they combine during chemical reactions by gaining electrons to fill the outermost shell. So if we have a metal combining with a non-metal, the metal will lose the outermost electrons. But the lost outermost electrons are gained, they are acquired by the non-metal. In the process of combination between a metal and a non-metal, both become chemically stable. They both become chemically stable by acquiring a full octet or a full outermost shell. So I'm saying silicon is a non-metal in group 4, in group 4 of the periodic table. And the atomic number of silicon is 14. Therefore, we write the ground state electronic configuration of silicon as 1s2, 2s2, 2p6, 3s2. Those are so how many? 12. Remember, they are 14 in silicon. So we are left with 3p2. 3p2. Let us run to 15, element number 15. The element whose atomic number is 15 is known as phosphorus, which is also a nanometal. Phosphorus is written with the capital P as its symbol. Phosphorus is a non-metal, is a non-metallic solid. It is not a gas. It's a solid element in group 5 of the periodic table. Whenever I say group 5, you should know that the outermost energy level in that case of phosphorus has 5 electrons. So the outermost shell has got 5 electrons in phosphorus, and the atomic number of phosphorus is 15. We are going to write the ground state. The ground state electronic configuration of phosphorus, we will simply write it as 1s2, 2s2, 2p6, 3s2, 3p, because these are already 12, and the atomic number says they are 15 electrons. So this is left with 3 to make them 15. So this means the 3p sub energy level is half full, because to be full, to be completely full, there should be 6 electrons at the p sub energy level. Whether it is 2p or 3p, it should be 6. So this means that n is equal to 3. The third energy level has got 8. Has got 5. 2 plus 3, 5 electrons, and that places it in group 5 of the periodic table. So n is equal to 3 has 5 electrons, hence group 5. Remember, the group number is equal to what? The group number is always equal to the number of electrons in the outermost energy level. Moving to sulfur. Sulfur is also a non-metal, a solid non-metal. It is a solid non-metal with a symbol capital S, and it is in group 6 of the periodic table. In group 6 of the periodic table. So we are going to write the ground state electronic configuration of sulfur, because we know that the atomic number, which is also the number of electrons of sulfur, is equal to 16. So we will write the ground state electronic configuration of sulfur as 1s2, 2s2, 2p, 6, 3s2, and 3p4. 3p4. We are left with only 4 elements to call it a day, and we are going to number 17, which we call a halogen, and its name is chlorine. Chlorine is a gaseous element, which we call a halogen. That word halogen, it means a salt maker. A halogen is a salt maker. It means these elements, like chlorine, bromine, fluorine, with group 7, they combine with metals to form salts. They combine to form salts. For example, sodium chloride, magnesium chloride, potassium chloride, calcium chloride. So halogens are actually salt makers because they combine with metals to form salts, which are called halides. Halides of metals, metal halides. So chlorine is a gaseous halogen in group 7. In group 7b of the periodic table. Of the periodic table. So what is the atomic number of chlorine? The atomic number of chlorine is 17. And therefore we are going to write the ground state electronic configuration of chlorine as 1s2, 2s2, we are now on energy level 2, 2p6, we've finished energy level 2. Then we go to energy level 3, 3s2 and 3p5. This means that when you look at the outermost energy level, the outermost energy level, the outermost energy level, N is equal to 3 in chlorine. It has how many electrons? It has 2 plus 5. It has 2 plus 5, which makes them 7 electrons. So there are 7 electrons in the outermost energy level of the chlorine atom. And this is why chlorine is placed in group 7, in the group of halogens in the periodic table. In the periodic table. It is coming to the end of our conversation. Number 18, element number 18. Remember, we are arranging these elements in the order of increasing atomic number from the smallest to the largest as they are organized in the modern periodic table. So element number 18, this one is also chemically inert, and we call it a noble gas, just like helium and neon. Argon is a noble gas in group 8. In group 8 or group O of the periodic table. The atomic number of argon is the atomic number of argon we write the symbol of argon as capital A, small r. So the atomic number of argon is 18. It is 18. And therefore, we write the ground state electronic configuration of argon as 1s2, 2s2, 2p6, 3s2, and 3p6. So when you reach a maximum of 6 in the 3p, stop feeding. It means the P sub energy level is already full with full orbitals. All the 3 orbitals at P sub energy level are filled, each with a pair. So you stop there. You stop there. Let me show this one for purposes of emphasizing the point that diagrammatically we will have 2 electrons here in that orbital full. 2 electrons in this orbital full. 3. Here we draw 1, 2, 3. With the 2 electrons there in one orbit of 2p, in another orbit of 2p, 2 electrons, and in another orbit of 2p, 2 electrons. So the 2p sub-energy level is also full. Going to 3s, we have 1 electron and 2 electrons with opposite spins. So 3s is also full. Let us go to 3p. Going into 3p also, remember we have 3p orbitals at this level. So the first orbital will be, remember we first fill singular. So we fill 1 electron there, another electron here, another electron here. So far those are 13. And then we fill here 14, 16, and 15, and then 16. So it means when you look at this element called argon, all the orbitals in that atom are completely filled with electrons. In other words, at energy level is equal to 3. At energy level is equal to 3. There are, at n is equal to 3, energy level, there is, or there are 80 electrons. What are those electrons? Those 2 at 3s plus the 6 at 3p. So that means it is full. It is a full octet. We call it a full octet. From the word octagon. Octagon is an 8-sided polygon. A polygon with 8 sides is called octagon. So when the energy level has 8 electrons, we call it an octet. It is completely full. It is completely full. The story is about to end. The conversation is about to end. Because argon has got a full octet, a full outer octet. There is a word you can add here which should not be left, which we should not leave behind. That word is outer, full outer octet. The full outer octet makes argon chemically inert. This makes argon chemically unreactive. Chemically unreactive. It makes the full outer octet makes argon chemically inert, meaning it can neither lose nor gain electrons from the outermost or into the outermost shell. It is already complete. The outermost shell is already complete. The conversation, our conversation now moves to the second last element, which is potassium. Potassium, since potassium is following argon, and argon is already full, so we are going to place potassium in group 1 again. Interesting. Potassium, symbol K. Potassium, symbol K, is an alkali metal. The word is not alkaline. The word is not alkaline, but we say alkali metal. These metals like sodium and potassium, they form alkalis, the soluble hydroxides of metals, the soluble bases, such as potassium hydroxide, sodium hydroxide. So those metals like potassium and sodium, which form soluble bases when they combine with water. When potassium combines with water, it will form potassium hydroxide if it combines with cold water plus hydrogen. When sodium combines with cold water, it will form sodium hydroxide and hydrogen gas. So the sodium hydroxide and the potassium hydroxide are called alkalis. And the metals which form those alkalis are called alkali metals. And they are mainly found in group 1 of the periodic table. We mainly know lithium as an alkali metal, sodium, another alkali metal, potassium, another alkali metal. But we also have others like rubidium and cesium. But at our level, we'll only talk about lithium, sodium, and potassium as alkali metals at this level. But there are others. So in this case, potassium is an alkali metal in group 1 of the periodic table. In group 1 of the periodic table. Remember, potassium K has atomic number 19. Atomic number 19 means, this atomic number 19 means that, potassium has one more electron, more than argon. Potassium has one electron more than argon, and that one electron will go in another energy level because the 3 is full. So we shall go to 4, and we shall begin with 4s. 4s. Therefore, the ground state electronic configuration, of potassium is 1s2, 2s2, 2p6, 3s2, 3p6, that is full. You move to another energy level 4, 4s1. 4s1. Now, when you look at the outermost energy level, which is n is equal to 4, the n is equal to 4 outermost energy level has only one electron. Has only one electron, which is the reason why this element potassium is placed in group 1, the group 1a of the periodic table. Because I told you that the group number is always equal to the number of electrons in the outermost energy level. So we can say hence K belongs to group 1a of the periodic table. The last element which you need to know. Remember, this is basic science. And the course is called Atomic Structure and Bonding. atomic structure, and bonding. When we go to the last element which I want us to talk about, this is calcium. Calcium. Remember, when we move from group 1, the next group we go to is group 2, meaning that the outermost energy level in this next element will have 2 electrons. It will have 2 electrons. And that is similar to potassium, whose outermost energy level had only 1 electron. So calcium, remember the symbol is capital C, small a. And just like magnesium and beryllium, we place this one in group 2, in group 2A of the periodic table. And all elements in group 2A of the periodic table are known as alkaline. Here we add there Ne to alkali. So we say alkaline earth. They are mainly found underground. Alkaline earth metals. So calcium is an alkaline earth metals. Remember, I emphasized this. Indicate the group number. Indicate the group number of the periodic table. Of the periodic table. Now, this element calcium, like the number indicates, it has atomic number Z equal to 20. Unlike the O-level format of writing electronic configuration, we are again going to follow the format which shows the arrangement of energy levels, sub-energy levels, and the orbitals in those sub-energy levels. And we will say that the ground state electronic configuration, of calcium will be 1 S2 2 S2 2 P6 3 S2 3 P6, and we move to the outermost energy level now, which is energy level 4. And remember, we begin with S. These are already 18. And we fill it by adding the remaining 2 to make them 20. This means that in the outermost energy level, n is equal to 4, there are 2 electrons only, for which reason the element is placed in group 2A of the periodic table. I want to end today's lecture by emphasizing some points. Number 1, we have been following these elements in order of their increasing atomic numbers, from the lightest, which was hydrogen, now to calcium. But there are others which we call transition elements or transition metals, such as scandium, vanadium, titanium, iron, molybdenum, copper, and others, which we know are found between group 2 and group 3 of the periodic table. Those elements, we've not discussed them here because they have some unique chemistry. Like they have variable oxidation states or variable valences. For example, you can find copper 1 and copper 2 salts. So that means copper does not exist in one oxidation state, but it has variable oxidation states or variable valences. We will not talk about that because there is another branch of chemistry that you will find, which we call transitional metal chemistry. We've not talked about iron, for example, because we know there is iron 2 and iron 3 salts. You have had iron 2 chloride and iron 3 chloride. That means iron can combine with other elements in different oxidation states. So we will discuss that chemistry later. We also know that the transition elements from 21, 20 to 23 onwards, they form what we call complexes. They form complexes and colored compounds. They form complexes and colored compounds. So they have some unique chemistry. Unlike these ones, mainly in group 1A, group 2A, and group 3, plus the halides and other nanometals which we've talked about, and those mainly form compounds, so solids, which are colorless or generally white solids. And my major emphasis today has been stressing the point that the atomic weight or the atomic mass is determined by the number of protons and neutrons in the nucleus. It is the nucleus of an atom which determines the atomic mass or atomic weight, not the electrons. The mass of electrons outside an atom is negligible, very small. So electrons only determine the atomic size. Electrons only determine the size of an atom, just like I've been indicating to you here as far as writing electronic configuration is concerned. A large atom will have more electrons, and the outermost electrons will be very far away from the nucleus and will be experiencing minimum or very low nuclear attraction. The positive nucleus will expose a smaller attraction to the outer electron, keeping the size of the atom large. But for a smaller atom, like that one of carbon, lithium, the outermost electrons are very close to the positively charged nucleus, and therefore they experience great nuclear attraction, hence keeping the size of the atom small. And to end the conversation, atomic number simply means the number of protons in the nucleus of an atom. And for an electrically neutral atom, an atom without a charge, the number of protons inside the nucleus is always equal to the number of electrons outside the nucleus in energy levels. We can also say that the number of positive charges inside the nucleus of an atom are always equal to the number of negative charges outside the nucleus of the atom. Mark those concepts clearly in your head. It is that relationship, number of protons with positive charges equaling to the number of electrons with the negative charges, which make the positive and negative particles cancel out. They cancel out one another. Positive 6 plus negative 6, you get 0. That makes an atom in its ground state electrically neutral. It is an atom is an electrically neutral particle of an element that can take part in a chemical reaction. Taking part in a chemical reaction by an atom means that the atom can either lose electrons from the outermost shell, just like the metals or the metallic elements do, or the atom may gain electrons to fill the outermost shell, just like the atoms of nanometals do. So that is the emphasis. Whenever we are talking about chemical reactions occur by either a transfer of electrons from an atom of a metal to the atom of a nanometal, or it can take place by sharing electrons between two non-metallic atoms. If the combination occurs by transfer of electrons from an atom of a metal to an atom of a nanometal, we call that electrovalent bonding. or ionic bonding. It is between a metal and a non-metal. And there is always a transfer of electrons from the outermost energy level of a metallic element, of the atom of a metallic element, to the outermost energy level of the atom of a non-metallic element. And the chemical union which is formed between the cation and anion is known as electrovalent bond or ionic bond. So an ionic bond is a strong electrostatic force of attraction between a positively charged cation and a negatively charged anion. That holds the structure of the compound in a kind of a crystal lattice. A crystal lattice. When we talk about covalent bonding, which I've said is simply sharing electrons between two non-metallic atoms of elements, a covalent bond between two non-metallic atoms is therefore a shared pair of electrons. So when we talk about covalence, it means sharing of electrons between the two atoms of non-metallic elements. And when we talk about electrovalence, it simply means the transfer of electrons from an atom of a metal to an atom of a non-metal. Those two are the most common forms of chemical combination, chemical union, or chemical bonding. Ladies and gentlemen, I would like to end by telling you what we called atomic mass. I didn't give you the definition, but atomic mass is also known as nucleon number. Nucleon number. And we define it as the sum of the protons and neutrons in the nucleus of an atom. The sum, the total sum of protons, of all protons and all neutrons in the nucleus of an atom is the atomic mass. And don't forget that there are some elements which we call isotopes. Don't forget the elements we call isotopes. You will find an element like chlorine having having two forms of atoms, like one atom may be 37, 17 chlorine, and another one may be 35, 17 chlorine, where the upper number is the mass number, or atomic mass, while the lower element is, the lower number is the atomic number. So some elements, such as chlorine, have got two forms of atoms. Where we have one with mass number 37, which we can call chlorine 37, and another one with mass number 35, and we can call it chlorine 35. But the element is the same. The element is chlorine, but having different mass numbers. Such atoms of elements with the same atomic number, 17, but different mass numbers, are known as isotopes. They are known as isotopes. So we define isotopes as atoms of the same element. With isotopes are atoms of the same element with the same what? With the same atoms of the same element with the same atomic number with the same atomic number, but different mass numbers. Or you could say, but different numbers, Newton numbers, but different number of neutrons. An example of isotopes is chlorine 35 and chlorine 35 and chlorine 37. Or you can write it as 35 as a superscript and then 37 as a superscript. But the 17, which is the atomic number, is kept the same. So those are called isotopes. We know other elements which show isotope. Another element which shows isotope, we know hydrogen. In fact, hydrogen has got three isotopes. Hydrogen, switch on. Hydrogen has three isotopes. This means hydrogen can exist as 11H, which we call normal hydrogen. So most of the gaseous hydrogen has 11H isotope. Then there is the 21H, which we call deuterium. It exists in a smaller proportion in a sample of hydrogen gas. And 31H is another isotope, which we call tritium. So these three are the known isotopes of hydrogen. What is common to all of them is that the atomic number is 1. Atomic number is 1 in tritium, atomic number is 1 in deuterium, and atomic number is 1 in normal hydrogen. But what differs is the mass number. Mass number in normal hydrogen is 1, in deuterium it is 2, and in tritium it is 3. Meaning that the atomic number is the same, the element is the same, but the mass numbers are different due to the differing numbers of neutrons. I wish to stop here. I remain John Bukenya from Makerere University, main campus, one of the coordinators of e-learning at Makerere University in the Institute of Open, Distance, and e-learning. Thank you very much for watching this video. I wish you good luck in your final assessments. God bless you.